My name is Akshara and I'm a graduate student, and I'm here to introduce you to the topic of stability analysis for topic models, which is a crucial aspect of text mining that helps us extract meaningful patterns from large data sets. Moving forward to the introduction, uh, let's see what topic modeling is. So, first, let's define topic modeling. It's a technique used to discover themes or topics within a large collection of texts. These topics can be represented in two ways as probability distributions over the words in the text, indicating how likely each word is associated with the topic, or as clusters where each word has a specific weight or importance. This forms the foundation of how we analyze and interpret large volumes of text data. The methods employed in topic modeling are probabilistic and non-probabilistic methods. So the probabilistic methods include latent wish list allocation (LDA) and probabilistic latent semantic analysis (PLSA). The non-probabilistic algorithms include the non-negative matrix factorization, which uses mathematical techniques to achieve similar goals like the probabilistic methods without relying directly on the probability. The importance of choosing the right number of topics K is very critical. If K is too low, our topics will be broad and vague, glossing over intricate details. Conversely, if K is too high, we face overclustering where topics may overlap, excessively complicating analysis. The ideal K can vary, showing that topics can exist at different levels of detail, from broad to very specific. Challenges in topic modeling. So, a significant challenge in topic modeling is ensuring stability. This means a model should consistently produce similar results, even if there are slight changes in how the model is initialized or in the data set itself. So, a proposed approach for this challenge is the term centric stability approach. This method focuses on the stability of the top ranked term across multiple runs of the model. We use a top weighted ranking measure where higher ranked terms exert more influence, ensuring that our model remains robust even when faced with data variations or different starting conditions. So, moving forward with the related work that has been done in a in a in this paper. So we have matrix factorization. So this specifically is called the non-negative matrix factorization. NMF plays a vital role in topic modeling by breaking down a document term matrix denoted as A into two matrices W and H. The matrix A representing terms by documents is approximated as the product of W, the basis vectors which can be read as topic, and H, which contains the document memberships. Our goal here is to minimize the error between the original matrix A and its approximation. So if the error is low, it retains more of the original data structure, enhancing the interpretability and meaningfulness of topics extracted from the texts. So an interesting aspect of NMF is the use of the residual sum of squares, which helps in determining the optimal number of topics by identifying the inflection point in the error curve. The next thing is the stability analysis. First, the application of perturbation techniques where we intentionally alter the data by sampling or modifying initial conditions to observe if the clustering results remain consistent. This method tests the robustness of the model against the changes that might occur in real world scenarios. Another significant aspect is the use of the consensus matrices. So, these matrices are powerful tools for visualizing and quantifying the agreement between different clustering outcomes. For instance, in the method developed by Brunet and colleagues for non-negative matrix factorization, we construct what's known as connectivity matrices. Each element in these matrices represent whether pairs of items are consistently grouped together across multiple runs. By averaging these connectivity matrices over several runs, they create a consensus matrix. The matrix then serves to visually and quantitatively assess the clustering stability. So we evaluate the stability using a metric called the cophynetic correlation coefficient. which is calculated from the hierarchical clustering of the consensus matrix. The stability of a particular cluster count or the number of topics in our context is then determined by observing the changes in this correlation coefficient. A sharp drop in the coefficient suggests a threshold beyond which increasing the number of clusters does not yield stable or meaningful separations. Lastly, we look at the ranking comparison. To measure stability, sorry, comparing ranked lists is fundamental in topic modeling, where terms are often ranked by relevance to the topic. Traditional metrics like Spearman's foot rule and Kendall's term measure distances between rankings, but they don't handle the indefinite rankings well, where items may not appear in both lists. To address this, newer metrics like average overlap have been developed, which provide a top weighted comparison. This means changes at the top of the list, where the most relevant items usually appear, have a large impact than changes at the bottom. Next, we move on to the methods that have been used. First one is the term ranking similarity. So here we see an illustration that shows the average Jaccard scores between two lists of terms. This table visually demonstrates how terms from different topic lists are compared at increasing depths to calculate a score that reflects their similarity. It's a clear example of how top terms align or diverge, which helps in understanding the impact of term relevance and list depth on topic similarity. Next, we look at the topic model agreement. So we here we look at the similarity matrix based on the similar. So here we look at the similarity matrix based on the average Jaccard scores between two topics from two different models. This matrix not only helps in visualizing the agreement levels, but also in explaining how we apply the Hungarian method to optimize topic matches, ensuring the best possible consistency between comparative models. Next, we move on to the selecting the number of topics. So we present a process. Here we see a steps outlined in evaluating the stability across multiple models and data samples to determine the optimal number of topics. This summary effectively breaks down the method of generating multiple topic models from sampled data, comparing them to different comparing them to a reference model and calculate mean agreement scores to determine the stability at each possible topic. This supports the discussion by providing a step-by-step guide to the analytical process, emphasizing how stability is assessed and the optimal number of topics is selected. So next we move on to the evaluation where we perform stability analysis on different data sets. So details. So here we can see the details of the different data sets that have been used for the evaluation. These include a mix of general and sports news from the BBC, articles from The Guardian, the Irish Times, and selections from the New York Times. Each dataset has been pre-processed and the terms occurring in less than 20 documents were removed and the data was normalized. This detailed preparation ensures that our stability analysis is performed on clean, relevant data with ground truth tables, providing a basis for measuring the performance of our topic modeling method. The graph on the right-hand side depicts stability scores across a range of values for K, which represents the possible number of topics. A higher score suggests more consistent topic identification across different samples. So next we will look at the correlation of the stability scores. So to fine-tune the model, uh, we examine the stability using different numbers of top terms 10, 20, 50, and 100. They found high correlation across all values, indicating that our stability scores are consistent regardless of how many top terms we consider. This gives confidence that the model's findings are reliable and not overly dependent on this parameter. We further look at the stability scores for all the data sets given. So we have 8 different data sets, and we can see the stability scores and so we can see a series of plots, each corresponding to a different text corpus. The blue line represents the stability scores for a fixed number of top terms, while the red line shows the normalized consensus scores. Each point on the x-axis represents a different number of topics k. Notice how the stability scores fluctuate as k changes. The peak signifies where the model finds a stable number of topics that best fits the data. So, for instance, the stability for the BBC dataset peaks at k equal to 5. This aligns perfectly with the actual number of distinct categories within the dataset, suggesting that our model is accurately capturing the underlying thematic structure. Conversely, with BBC Sport corpus in figure 4b, the stability peaks at k equal to 4 and then slightly lower at k equal to 5. This indicates a slight amalgamation of topics in the smaller categories, which is also supported by the consensus approach. So, looking at 5A and 5B for the New York Times datasets, we see some interesting patterns. There are troughs for certain values of k which deviate from the expected ground truth labels. This reveals instances where topics may be conflicting or divided inconsistently, offering insights into the complexity of thematic structures within these data sets. Let's look at the discussion and interpretation of our results uh, in the previous uh, from the previous graphs. So we reflect on the intriguing observation that multiple datasets show significant agreement at k equal to 2, suggesting a tendency towards broader categorizations rather than the finer distinctions one might expect. This phenomenon highlighted here often represents often presents as one dominant merged topic alongside a small outlier topic within the data, as demonstrated. So now let's take a closer look at table 4. For example, in Guardian 2013 corpus with k equal to 3, the topics are broad, merging culturally related sections into single topics. Conversely, in Wikipedia High with k equal to 4 shows distinct topics such as music and sports reflecting more defined content categories. These examples underscore that the ground truth labels don't always mirror the nuanced structures covered by topic modeling. Importantly, we found that the stability analysis not only yields meaningful insights into the optimal number of topics but also offers computational advantages. Unlike the consensus matrix based methods that require intensive hierarchical clustering, our stability analysis can be parallelized, allowing agreement scores to be computed independently for each factorization result, leading to significant time savings. This enhances the method's scalability and applicability to large data sets. So next, moving forward, we'll go to the conclusion. So as we reach the conclusion of our presentation, let's reflect on the key contributions of our work. So we introduced a novel method for selecting the number of topics in topic modeling, which centers around a term-centric stability analysis strategy. The approach looks for agreement between the most important terms in topics generated from different samples of the same dataset, identifying the most suitable number of topics K. Through extensive evaluations across a variety of text corpora, the findings indicate that this method offers a valuable guide for determining one or more appropriate values for K, aiding in the distillation of information into coherent and interpretable topics. Usually, the method's reliance on term rankings rather than raw matrix factors or probabilities paves the way for its application across a spectrum of topic modeling techniques, including probabilistic methods like LDA and even traditional clustering algorithms like K-means. Looking ahead, uh, we could even explore the application of stability analysis in concert with a broader array of algorithms, expanding the method's versatility and enhancing understanding of topic modeling's potential. This promises a significant step forward in the capacity to extract meaningful patterns from complex data sets, a cornerstone of modern data analysis. Thank you.